Those are both X's you can't use. Now, discontinuities and rational functions are either removable or non-removable, right? They're removable, the factor cancels out. They're non-removable, it doesn't cancel. Can we cancel anything here? That factor cancels, so x equals 4 is removable then, right? We've removed it. X minus 5 is still there, so it's non-removable. If it's removable, then it's not a vertical asymptote, it's a 1. So there's a hole with x equals 4. The non-removable is where you have a vertical asymptote. So there's a hole at x equals 4, there's a vertical asymptote at x equals 5. Yours okay? And the last one, there's only one discontinuity. What is it? What makes this denominator 0? So it's discontinuous at x equals 1. Will x minus 1 cancel with a 5x cubed? No. So that's going to be non-removable, right? There's no way to cancel it out. And since it's non-removable, then it's a what? Vertical asymptote. The only reason I'm writing all these little notes about removable and non-removable, I'm trying to make it make sense of it, right? Okay with the vertical asymptotes. I put examples of every possible thing there. Now, the way you determine horizontal asymptotes is totally different, right? It's all about the degrees. If the top degree is higher, there's not one. If the bottom degree is higher, it's a 0, right? If they're the same degree, it's the ratio of leading coefficients. And you just have to learn those rules. Now we're going to go through and do all the horizontals. We just went through and did all the verticals. So the first one, what's the degree of the numerator? What's the degree of the denominator? 1. So the horizontal asymptote, when the degrees are the same, is that y equals the ratio of leading coefficients. What's that going to be here? 2 over 5. So there's a horizontal asymptote at 2/5. Okay? Going vertically, what's the degree of the top? What's the degree of the bottom? 1. When the top degree is higher, there is no horizontal, right? So there's no horizontal asymptote. That's why you use HA for horizontal asymptote. Yours okay? The third one in the first column, the degree of the top is 1, the degree of the bottom is 2. When the bottom degree is higher, where's your horizontal asymptote?
0.
Y equals 0. And it should be y equals 0, not just 0, because this is the equation of a line. Okay, so don't forget the y equals or the x equals when you're giving asymptotes. Next column. The degree of the numerator is 1, the degree of the denominator is 2, bottom degree is higher, where's your horizontal asymptote? Y equals 0, right, when the bottom degree is higher. Now this one, the simplified form is what? X plus 1 over x minus 5, I think. Is that right? X minus 4, x plus 1, x minus 4, x minus. Yeah, okay. The degree of the top here is a 2. The degree at the bottom here is a 2. Same degree, right? In the reduced form, the degree of the top is 1, the degree of the bottom is 1. Either place you get the same thing, don't you? The degree of the top is the same as the bottom. So where's your horizontal asymptote at? Y equals the ratio of the leading coefficients. So 1 over 1, which is 1, right? Now the rules for the horizontal are on the PowerPoint in section 3.5, if you wonder where these are coming from. last one. What happens when the degree of the top is greater than the bottom, as far as horizontal asymptotes? There's not one, right? No horizontal asymptotes. Everyone okay? Alright. Now, can you put all that together and sketch a graph of a rational function? So we'll have, there's no factoring and canceling on this one, right? So there is a vertical asymptote where? X equals 3. So you wanna say x equals 3, vertical asymptote. Everyone agree? It's not removable, it doesn't cancel out, right? So it's a vertical asymptote. Where's the horizontal? Y equals what? 2. Degree of the top's the same as the bottom, right? So it's a ratio of leading coefficient, so 2 over an understood 1. In a rational function, to get the x-intercept, remember in class I said really all you have to do is set the numerator equal to 0, right? If you set the function equal to 0, when you cross multiply, the denominators can go out anyway, isn't it? So to find the x-intercept in a rational function, just set the numerator equal to 0. If you set the whole fraction equal to 0, you'll get the same thing, won't you? Because when you cross multiply 2x equals 0, so that's why it works. So in a rational function, it doesn't apply always, but in rational functions, to get the x-intercept, you can just set the numerator equal to 0. And if I divide by 2, x equals 0. So there's your x-intercept, right? So it's going to hit the x-axis at 0, which is at the origin, right? Which means the y-intercept is going to also be 0, isn't it? Right? But anyway, to get the y-intercept, what do? You evaluate the function at 0, right? So if I were to put 0 in for the x's, 2 times 0 over 0 minus 3, isn't that just 0? So if I started my graph now, I'll have a vertical x equals 3, so I put that in. There's only one vertical, so this graph's going to be cut into 2 parts, isn't it? I have a horizontal at y equals 2. So I kind of have an idea about the basic shape, right? I know it goes through the origin, you agree? Because the x and y intercept are both 0. That's the only point I have, isn't it? So plot some additional points. I'm just going to do a little table and get a few more points. And the goal is to not have to do too many, because you know the basic shapes, right? So we already have x equals 0. Gives a y of 0. So let's get a couple below and a couple above. Actually, let's go one below, so maybe a negative 1. Let me go 1 below 0, so maybe what, negative 1? Then let me get the 2 in between 0 and the vertical asymptote. So I'm going to go ahead and do the 1 and the 2. And then let me get a couple on the other side of the verticals, maybe 4 to 5. And you may need these few points, right? Wherever your vertical asymptote is, right here, you need some points on the left of it and on the right of it. So you know which block to put your graph in, right? If I put a negative 1 in for x, what's y? It's 2 times negative 1 over negative 1 minus 3. That'll be a negative 2 over negative 4, which is positive 1/2. Do you agree? If I put a 0 in, I know that's a 0. We already found that. That was just a x and y intercept. If I put a 1 in for x, that'll be 2 times 1 over 1 minus 3. So that's 2 over negative 2, which is negative 1. If I put a 2 in for x, that's 2 times 2 over 2 minus 3. what's that, 4 over -1, so -4. If I put a 4 in for x, 2 times 4 is 8. 4 minus 3 is 1, so that's just 8, isn't it? And if I put a 5 in, 2 times 5 is 10. 5 minus 3 is 2, 10 over 2 is 5. And again, you may not need to get those many points. So if I plot my points from, so -1 up a half, 0, 0, 1, -1, 2, -4. Do you see what's happening in that block? It's going to, towards the left, it's gonna approach your horizontal, and to the right of that's gonna approach your vertical, right? Which is just the basic shape of those. That's why I said you may not need that many points. And then we jumped over the asymptote and went to what? Over 4 up 8. Over 5 up 5. You see what's happening there? You know, they're going to kind of look the same, right? The parts. So to the left, it's going to be approaching the vertical here, then coming down this way, it's going to approach the horizontal. And that's just the basic shape of a rational function, right? Should be touching the horizontal, but you know, just kind of leveling off over this way. Any questions? So you will have to graph something like that by hand. And then, like I said, I might give you another one that's multiple choice. Where if you can find the asymptotes, plot a couple points, you'll be able to figure out which one's points. Okay, so then we went to section 3.6, solving polynomial inequalities. The steps were, because of time, I'm not gonna do both of these. They're pretty much just alike, just one's less than, equal to, one's greater than, right? And that just amounts to whether you put brackets or not. Let's do the first one. Step 1, let's get all the terms on one side. So I'm gonna move the 5x and the 2 over, and that'll leave nothing on the other side, right? Get everything to one side. Then set your polynomial equal to 0. This, before then, we would call this finding the x-intercepts, right? Or the zeros. Now we're calling it finding the boundaries, but it's the same math process. That's just a quadratic equation, isn't it? Does it factor? For 3x squared, your only choice is 3x times x, right? 2 is also prime, so my only choice is 2. For 2 is 2 times 1. If I need a -5 in the middle, so I'm gonna put the 2 here and the 1 here. Then a -2 plus 1. If I check my middle term, -6x plus 1x is -5x. So the factor is equal to 0. Solve these two, and that gives you your boundaries, or your boundary values. This will give me 3x equals -1, or x equals -1/3, and then this will give me x equals 2, right? So these are your boundaries. Why are they called boundaries? That's a place where the either is greater than 0 or less than 0 changes, right? Because those are the places where it equals 0. So it's either going to be less or greater, but it's not there, is it? And as a suggestion, this was just a suggestion, I said locate the boundaries on the number line, because we're not worried about the graph, we're solving an inequality. If here's 0, if here's -1, if here's +2, if I locate those boundaries on a number line, maybe -1/3 is about here, and then +2 is here. Think of it as cutting the number line up into sections at those boundaries, right? And writing those sections as intervals. So this first interval, left forever is what? -infinity up to the -1/3. So there's one interval, right? I know -1/3 is equal to 0. What happens to the left of that? Is it more or less? And then I have an interval between what? The -1/3 and the +2. And then I have an interval from 2 to infinity. So I call these the test intervals, right? You're gonna test these to see which ones work. And then you pick a point or value in each interval to test, right? You can pick any number between negative infinity and negative 1/3, except negative 1/3. That's why I said between, right? You could use negative 2 million, you could use negative 10,000, you could use negative 2, you could use negative 1, you could use negative 2/3, to make it easy on yourself. What do you wanna use? What do you wanna use for the testing? I would use negative 1. You want to understand that? That's why I said maybe a number line helps. Some students might have trouble thinking about a number in that interval unless they can see it. Now the next interval, I can use any number between negative 1/3 and 2. 0 is the easiest. You could use a 1, that's not too bad either, right? But 0 is definitely the easiest. And then I can use any number above 2. X equals 3, right? Or 4, or 5, or 10. Powers of 10 are easy too. So these are our values we're going to use for testing, right? And you're just testing to see if it makes a true statement or not. So I'm going to say testing. You don't have to label it out like this. This is just for your notes because it is a process, right? If I'm testing a negative 1, I can go back here or I can go here. It's the same inequality. Would you rather test in the original form or the everything on one side 0 form? What do you think? Which one would you use when you were testing? This one? Okay. So if we plug a negative 1 into that, I'll have 3 times negative 1 squared minus 5 times negative 1 minus 2. Is that less than or equal to 0? It's just yes or no. Yes, it works. No, it doesn't work. Negative 1 squared is what? 1 times 3 is 3. Negative 5 times negative 1 is positive 5. 3 plus 5 minus 2. 8 minus 2. Is 8 minus 2, which is 6, less than or equal to 0? No. So that means these numbers are not going to work. Now if I'm testing the 0, if I use the same inequality, the rewritten form. If I put a 0 in, you can do that in your head, can't you? If you replace the x's with zeros, isn't that going to be 0 and that going to be 0? So you're going to have what, negative 2? Is negative 2 less than or equal to 0? That's a yes, right? So these numbers work. And if I put a number in above 2, like 3, is 3 times 3 squared minus 5 times 3 minus 2, is that less than or equal to 0? 3 squared is 9 times 3 is 27. 27 minus 15 is 12. 12 minus 2 is 10, right? Is 10 less than or equal to 0? No. That's not true, so these numbers don't work. So now your answer. Your answer is either going to look just like this, or we might have to change the brackets, right? And that depends on the inequality. So brackets or parentheses.
When would the circle be closed?
When would the circle be closed? Which one?
Like on the graph line?
Well, I always, when I draw that number line, I'm going to leave it open because I'm waiting for that testing whether it's closed or not.
Oh.
Right? Because your answer is an interval, right?
Mm-hmm.
So do we change the brackets or not? Yes, because inequality says less than or equal to, right? Aren't those numbers the numbers that made it equal to, right? And then in between will be the numbers that make it less than, right? So that's why we changed the bracket. So the final answer on this one then, the solution to this inequality is the numbers from negative 1/3 up to 2, including those end values. Again, we're changing to a bracket because your inequality said less than or equal to. Now, if it just said less than, I would've left it parentheses, right? So because it's less than or equal to, these open dots actually could be closed. But the answer I'll be looking for is the interval, not the graph. You know, if I graph, the answer would be, you know, if here is negative 1/3, and up here is 2, it would be here, here, and everything in between, right? That would be a graph of the interval. And then when you get in the calculus, you hardly use the open and closed dots, you put brackets on these instead of open and closed dots. But they mean the same thing. Okay, so be able to solve a polynomial inequality. Section 4.1 is pretty much just, you know, graphing exponential functions, right? So different type of function, a function with a variable, the exponent, an exponential function, and then be able to use your calculator to evaluate some exponents that are hard, right? I would expect you to be able to look at that base and know that that graph looks like this, right? If the base is greater than 1, it's increasing. If the base is between 0 and 1, it's decreasing, right? Those are facts. Those are on the PowerPoint from that day we covered this if you need to go back and view that. But let's just plot a few points. We know exponential functions. We didn't do any transformations, right? I said we're just doing the basic ones because really we're just leading into the finding logarithms. We're going to have a horizontal asymptote at y equals 0. And that's just something you memorize. It's not because it's a 0 in the denominator or anything. It's all back to the definition of what it means to be a horizontal asymptote. As x goes to infinity or negative infinity, if y approaches a number but never touches that number, then it's a horizontal asymptote. So I know there is a horizontal asymptote at y equals 0. That's one of the facts. I know the domain's all real numbers, right? You can use anything you want to for x, but the range won't be all real numbers. Let's just plot a couple points. If x is negative 1, 0, and 1. Since we know the basic shape, we don't have to get too many points. If I replace the x's with those values, what is 3 to the negative 1 power? 1/3. What is 3 to the 0 power? 1. And then 3 to the first power is 3. So if I plot those points, left 1, up 1/3, try to squeeze that there, that looks more like a half, but you, above the x-axis, right? 0, 1, there's your y-intercept, over 1, up 3, you can start seeing the exponential growth. So it's gonna, you know, go off like that, and this way it's gonna approach the horizontal but never touch it. And like I said, from the beginning, I would hope you knew that that's what it was gonna look like. Now the next one, I'm gonna use the same x values. What is 1/3 to the negative 1 power? 1/3 to the negative 1 is 3. What is 1/3 to the 0? 1. And then 1/3 to the first, of course, is itself. I'm gonna plot these in black and use the same grid. Negative 1, 3. I'm gonna erase this one off. Negative 1 up 3. 0, 1, there's your y-intercept, over 1 up 1/3. So in this one, this way it's growing exponentially, this way it's approaching your horizontal asymptote. Right? And I said at the beginning, because the base is between 0 and 1, you should know it looks like that. Just get the points to get it in the right spot. Okay?
How did you get the horizontal asymptote?
It's just a fact about it.
Oh.
You don't algebraically get it, you just remember. If we had time, I would let x go to negative 10 million and show you that the y is getting close to 0, but not touching it. Calculators. If you have your calculator, practice. Do not miss these because you don't know how to use a calculator. e to the 1.2 power. Find your e to the x key, and put 1.2 in for the exponent, right? Where you gonna get it? Let's just round to the tenth place. 3.3. 2 to the square root of 7 power, so 2, I use the caret because it's easy, up arrow, and I'm gonna put square root of 2 in the exponent, so second, square root of 2, close parentheses, enter. What are y'all getting? To one decimal. Oh, I put a 7 instead of a 2, hang on. I put it 2 instead of 7, I mean, for the exponent. Now, 6.3, sorry. Pi to the e power, so I'm gonna hit my pi key, I'm gonna hit my up arrow, and then to get e in the exponent, I'm gonna do e to the first power. So I'm going to go to my e to the x is above ln, so I'm gonna do second e to the x, but put a 1 for the exponent. E to the first would just be e. So what are y'all getting there? 22.5 to one decimal. Square root of 5 to the e power, so second, x squared is how I get to my square root, 5, close parentheses, get up to the exponent, using the arrow, and then again I needed e to the first power, so I would get e to the x, and I'll put a 1 for the exponent. What are you getting there? 6.3 to the fifth, so 6.3, caret, 5, nothing tricky about that one. To one decimal, 9,924.4. What about 9 to the 1/2 power? You don't need a calculator for that, do you? 9 to the 1/2 means the same thing as square root of 9, doesn't it? Which is 3. So maybe just make sure you get those answers down, so you can practice if you struggled with your calculator on those. We did some more in class the day we went over this, that you hopefully have in your notes. Okay, now converting from log form to exponential form and exponential to log form, it's a formula, right? Y equals log to the base b of x, that's log form. That same expression in exponential form is what? B to the y equals x, right? Remember, what a logarithm equals is the exponent. So you do need to have this memorized, hopefully you already do. Okay, the first one, I'm going to change it to log form, so it's going to be log to the base what? What's the base? What's being raised to the power? 3. The power is the 4, right? So log base 3 of 81 equals the power. Remember, an exponential expression is like 2 cubed. This is the base, right? This is the exponent. This is what it equals, which we call also the argument. Notice in log form, it's the what? It's the exponent on the equal side, right? So this one, this is log base what? What's your base here? E of 12 equals the exponent. Log base E has a special name, right? Called what? Natural log or ln. So instead of log base E, I would just write ln 12. Log base E is what it means. You'll always see it written as natural log. Next one, log, what's your base? 10 of 10,000 right? Log base 10 is also a special log, it's called a common log. So you'll see that one written without the subscript, so just log 10,000. This is not wrong, this is just understood, right? Kinda like 2/4 is what it is, right? Same answer. I told you when working with logarithms, if you have a radical, write it in exponent form first. The square root is the same as what power?
1/2.
1/2. So 25 to the 1/2 power equals 5. That's the same expression, right? That's where it was a rational exponent. And what would that be in log form? Log to the, what's the base? 25 of 5 equals the exponent. That is converting from exponential to log form, and it's just a formula, right? Can you go the other direction? Same formula, just the other direction. These are all in log form. Can you change these to exponential form? In exponential form, the argument equals, ln means log base what? Ln is log base e, right? So your base is e and your exponent is a. So x equals e to the 8th, or e to the 8th equals x. Doesn't really matter which side you put which on. So the next one, argument, which is what, tenths, hundredths, thousandths, 1/10,000th, equals, what's the base? If I don't put a base and it says LSU, it's understood to be base 10, right? So 1/10,000th equals 10 to the -4 power. Here's your base, here's your power, here's what it equals, right? So the next one, argument x equals base 3 to the power of 4. Next one, 2 to the x power equals 16, right? Or 16 equals 2 to the x. And then the last one, x to the second power equals 25, or 25 equals x squared. So again, those last two slides, we're just using formula to go from one form to the other. So make sure you know that formula, right? If I'm ever evaluating a logarithm without a calculator, it's whatever the base is, right? What power do you need to raise the base to get the argument? That'll help you come up with the answer without a calculator, right? You gotta think, your answer is the exponent. When you evaluate a logarithm, you're having to come up with what the exponent was. So in the first one, natural log e. Natural log, ln means log base e, right? So e to what power is e? 1. Right? That's actually a property, isn't it? If the base and the argument are the same number, the answer is always 1, isn't it? So log base 5 of 5, 1. Log base 6 of 6, 1. The next one doesn't have base showing, so it's understood base 10, right? So I'm thinking 10 to what power would make it 1/10,000th? 10 to what power is 1/10,000th? What if it had been 10,000? 10 to what power is 10,000? Wouldn't it be 4 power? 10 times 10 times 10 times 10? So to make it 1 over that, instead of 4, make it what? -4. Right? 10 to the -4 power is 1 over 10 to the 4th, which is 1/10,000th, and that's just the decimal form, isn't it? The next one, your base is 3, your argument is 81, your answer is the power. 3 to what power is 81? 3 to what power is 81? Now you don't have to write write this down, this is what you're thinking in your head. What's the power? How many times you multiply 3 to get 81? 3 times 3 is 9, 27, 81. So your exponent will be 4, right? When you evaluate a logarithm, your answer is the exponent. The next one, 2 to the what power 16. Think of it this way. This is a base, right? This is the answer. 2 to what power? We'll raise it up to that, right? What will make this become this? What power? 2 to what power 16? 4, right? 625 to what power is 25? 625 to what power would take it down to a 25? So not reciprocal, not 1 over, but just a smaller number. If you were here in class that day, we said that's always going to be a fraction exponent, isn't it? What's the square root of 625? Isn't the square root of 625 25? So what's the power of it? 1/2. And there's no reason to miss that. I said you can use your calculator, right? Log base 9 of 81. 9 to what power is 81? 2, right? Log base 3 of 3. 3 to what power is 3?
1.
1, right? The base and the argument are the same. The answer is always 1. Log base 5 of 1 means 5 to what power is 1? If the base is whatever, but the argument is 1, the answer is always what? 0. Right, these are properties. These are on the handout that I gave you. Log base 3 of 3 to the 9th, that's an inverse property. If the log, base, and argument are the same number, then the answer is just going to be whatever that power is, right? Log base 3 of 3 to the 9th will just be 9, because those are inverses of each other. They undo each other. Log base 2 of 128. How many times you multiply 2 to get 128? 2 times 2 is 4, 8, 16, 32, 64, 128, right? 7. Log base 49 of 7. So your base is 49. Your argument is an integer that's smaller. It's got to be a fraction power, doesn't it? What's the answer? Think about how you make a 49 become 7. What do? You take the square root of it, right? Is the square root the same as the 1/2 power? Log base 6 of 1 over 36. And if that had just been log base 6 of 36, the answer would have been 2, right? The 6 squared is 36. To make it 1 over 36, just make it a negative 2. Natural log of 1. Natural log means log base e. Doesn't matter what the base is. If the argument's 1, the answer is what? 0, right? 5 to the log base 5, inverse properties. 5 to the log base 5 of 7, what's the answer going to be? Just 7. Every one of those could have been done on the calculator though, couldn't they? If you're not sure how to say, put this one in the calculator. Log base 625 over 25. And you don't have a calculator that lets you enter different bases. Everyone has a natural log key, right? Everyone has a log key. All calculators, all scientific calculators have those 2 logs. If you don't have a calculator that lets you enter, a different base and a different argument, then you can use the change in base formula, right? So I can write that as either natural log 25 over natural log 625, or I also have a log key. I could have done log 25 over log 625. The change of base formulas on your formula sheet that I gave you in class is also in the section on the company, right? Either one of those, when you type that into the calculator, you're getting 0.5, aren't you? You don't have to do both, just this one or this one, because those are the 2 calculator keys you have. Is everyone getting 0.5? Which is a half, right? So like on this one, I could have done log 128 over log 2. Notice the log of the upper one over log of the lower one, right? I could have done natural log 128 over natural log 2. And either way, actually goes that way. So even though I say evaluate without a calculator, I'm not gonna take the calculators away from you, so don't miss those, right? Okay. These say evaluate with a calculator, so that must mean I can't do these in my head, right? 3 to what power is 75? Well, 3 times 3 is 9, 27, 81, somewhere between 3 and 4, isn't it? If I wanna use the change of base formula, I can write that as what? I can either do log or natural log. Everyone understands you don't have to do both, right? Just pick one or the other. So I'll go with natural log this time. So I could do natural log of 75 over natural log of 3. And then let's just round off to 1 decimal. So natural log ln 75 close parentheses divided by ln 3 close parentheses equals 3.9, right, to 1 decimal. And I said it was somewhere between 3 and 4, right? So in the next one, I could do either natural log or common log. I think I'll do common log this time. So I'm gonna do log of 45 over log of 12. This change of base formula allows you to evaluate any logarithm on your calculator if your calculator doesn't allow you to enter different bases, right? So this time, I'm gonna do log, but you could have done natural log. Log 45, close parentheses, divided by log 1.2, close parentheses, equals, and to 1 decimal, 20.9. Doing okay? So log base 4 of 36, I think I'll go back to natural log. So natural log 36 over natural log 4. Let's round off to 1 decimal. Natural log 36, close parentheses, divided by natural log 4, close parentheses, 2.6. Log base 9 is 60, so I'm gonna do common log this time, so log 60 over log 9. And we'll round off to 1 decimal. Log 60, close parentheses, divided by log 9, close parentheses, 1.9. Now the last ones, I don't have to use change base formula to do them. Because don't you have a natural log key? So just do ln 5. ln 5, close parentheses, equals about 1.6. You would agree? Natural log 2/3. So natural log 2 divided by 3, close parentheses, equals negative 0.4, 1 decimal. You would agree? And then the natural log of the square root of 15, so natural log, second x squared to get my square root, put the 15 in, close the parentheses, close again, 1.4. Okay? So just make sure you practice your calculators so now you have the correct answers to several. Just practice. Okay, and then we have the expanding condensing properties. For us, it's just being able to use formulas, right? I mentioned in Calculus 1 we use these properties when we're taking derivatives or integrating. First one is not too bad, it's the log of a product. That's the product rule. That expands to a sum, right? So that would be log base 3 of x plus log base 3 of y. The next one involves the power rule. The power rule just says you can bring down the exponent and multiply. So then that would just be 4 times log base 2 of n. The next one's a couple properties. First I have a power rule, and then I have a product rule on it. So I could bring that 3 down first, so it'd be 3 times log base 3 of x times y. And then log base 3 of xy, that's the product rule, so that expands to a sum like the first one. So we already done that in the first one. So it'd be 3 times, it's gonna be times both of those. So I think I'll put a bracket here and then distribute. Log base 3 of x plus log base 3 of y. And then if you pass out the 3 log base 3 of x plus 3 log base 3y. And that will be completely expanded. Other option would have just been said x cubed, y cubed, right? And then separate and then brought the 3's in. So the next one, the big picture is a quotient, this over this, right? So quotient rule expands to a difference. So log base 5 of 3 times x minus log base 5 of y. And the log base 5 3x, that's a product rule, right? So that'll expand to a sum. So log base 5 of 3 plus log base 5 of x minus log base 5 of y. And that would be completely expanded. The next one, we said in class, if you're working with logarithms, you have a radical, write it with an exponent, right? Square root's the same as what power? 1/2 power. So x, y over z, all to the 1/2 power. And I'm gonna do the power rule first. I'm gonna bring down the 1/2. So 1/2 times. Isn't the log of this, that's a product, right? That would expand to a sum. So log base 3 of x plus log base 3 of y over, sorry, minus log base 3 of z. So the top part's product rule, the quotient rule makes that last term minus, right? And then I could distribute the 1/2. You could all do that, right? Just pass out the 1/2. That's called expanding. And then the reverse of that is condensing. And like I said in class, it just depends on what you're doing in calculus. Do you need expanded? Do you need condensing? So first it's just algebra, right? And formulas. Could you put these back together? Could you condense these back to a single log statement? Okay, the first one, this is the plus. That's the product rule in expanded form, right? So if I condense it, it'll just be log of what? X times y, right? That's it. On this next one, these numbers in front would have been exponents. So I'm gonna put those back up first. So that would be natural log of 3 to the 7th minus natural log 5 to the 8th. So I use the power rule in reverse there. And since this is minus, that will go to a quotient, right? So notice if I put it as a quotient, I just write natural log once, not twice. Natural log of 3 to the 7th over 5 to the 8th. So in condensed form, it should only have one log, right? I've seen students put log over log. You're mixing up the change of base formula with these properties if you do that. Okay, so left to right, this is a plus. So then these two would apply to the product rule, right? So I condense that to log base 3 of x minus 2 times y. And I still have this minus log base 3 of z. So I condense the first two terms in the first step, right? Now since this is a minus, then I can apply the quotient rule. And that would end up being log base 3 of x minus 2 times y over z. The next one, exponents, I'll put those back up first. So natural log x minus 5 to the 8th minus minus natural log x plus 3 to the 7th. And then since it's subtraction, that's quotient rule. So natural log of x minus 5 to the 8th over x plus 3 to the 7th. Now the next one's a little tricky because that 1/2 is out in front of the parentheses, right? So let's do inside first. So inside, that's a plus, so that's product rule, isn't it? So that would be 1/2 times log of x times x minus 7. Everyone agree? And then the 1/2 will go back up in the power, right? Or I could have distributed the 1/2 to both. So then that will end up being log of what? X times x minus 7 to the 1/2 power, which is the same as the square root. Agreed? And that would be completely complete. That's it. Do you recognize that graph? I gave you this one. And all I told you there was that was the inverse function. Could you tell me what the function is? It's just the inverse of the one I gave you, right? If you had to find the inverse of f of x equals 2 to the x, replace f of x with y, swap the x and y, resolve the equation for y. How would I take this and write it so that y is by itself? Don't say divide by 2. This is not an algebraic function, is it? It's an exponential function. What's the inverse of exponentials? Logarithms, right? So if I want to get the y by itself, then I just change that to log form. So in log form would be log base what? Log base, what's your base? 2 of x equals the exponent, right? That's just that formula to go from one form to the other. That's the inverse. So then replace y with inverse notation. So that's actually what that function would be. What's the domain of the exponential function? The blue. It's all our numbers, right? What's the range? The y's are not getting to 0, so there are numbers above 0, so 0 to infinity, right? And there's a horizontal asymptote at y equals 0. It's an exponential function, right? And what about the purple? If the domain of this is all our numbers, that's going to be the range of this one, isn't it? Because when you graph inverse functions, don't you just swap everything, x and y? So that's going to be the range here. Just think about the y's. They're going down forever, and they're going up forever slowly, but they are going up, aren't they? And then what would the domain be? The same as the range here. Remember, you can't take the log of 0 or anything less, right? You can only take the log of positive numbers. This is just a picture of line. This has a vertical asymptote at x equals 0. Right? And we do it like that in class. Just want to see if you recognize